there's a couple different types of error that you have to deal with Taylor polynomials, and they tend to be a little bit of a tricky topic. The easiest one is the actual error, and this is the real amount of error. This is just you take your actual value and you subtract the Taylor approximation, and you get how far off the two are. So what you do is you basically take your f of x and you get the actual value. So for the example down here, we're going to find sine of 0.1, which I do over here on the right. So sine of 0.1 is 0.0998. Okay, couldn't tell you what that was off the top of my head. I could tell you what sine of 0, things of parts of pi, that's perfectly fine. And then after you found that value, you do also the Taylor polynomial. So you plug the x value into the Taylor polynomial and you get another value. So we're going to use the Maclaurin polynomial, or the third degree Maclaurin polynomial, to approximate it. So I wrote down here what the third degree Maclaurin polynomial is. If you have trouble finding that, you can go back to my other video and watch through it. But this is basically our Maclaurin polynomial. And we're going to find p sub 3 of 0.1. So you plug in 0.1 everywhere you see x, and you go for that. That's my first line over here in the calculator. So I got 0.1 minus 0.1 cubed over 6. That's our 3 factorial. And we get the value of 0.0998. Now, if I look at these two numbers, up to the first 5 decimal places, they're accurate. So the actual error is very, very small. So when I subtract them, I get 8.33 times 10 to the negative 8. That's a very accurate amount. Now, accuracy is always a relative thing. If you're talking about being like 2 inches off, there's a big difference if you're talking about being the distance from here to the sun and the distance from one piece on your paper to another piece on your paper. So you also got to talk about the relative error. But this and just straight up error is pretty darn small. You can see these two are accurate to 4 decimal places, 5 decimal places, what we said, 1, 2, 3, 4, 5, no, 6 decimal places. Jeez, I can't count. So, and then the 7th, you're only off by 1 on that. So it's a very accurate thing. And subtracting the 2 lets you find that value pretty quickly. Alternating series is actually a very easy example of how to find an error bound, or your worst case scenario. What happens with alternating series is every single term, they kind of correct each other. So you start out pretty high at 1, and then you take down a half, and it gets closer. And then you add a third, and it gets closer. You subtract a fourth, and it gets closer. You add a fifth, and it gets closer. Subtract a sixth, and it gets closer. Every single time it gets closer. So the worse you really are is kind of how far off the last term was. So all we have to do is we want to take the absolute value of the next term. So if I'm looking at finding the error bound, so the function is approximately wherever we stop. So if we're looking at the 5th degree, the error bound would be the absolute value of the next term, negative 1 over 6. So it's going to be plus or minus 1 over 6 from the actual value. So when you compute this, your actual value is going to be about whatever this becomes, plus or minus 1/6. The error bound is just that number. Let's see if we get a couple more examples here. So in number 3 here, we want to find the error bound for this series, stops at 5, as compared to the infinite series. So the infinite series would be the perfect version. Of this, we're only talking about the 5th. So where does it stop? At the n plus 1 term. So what we have to do is the absolute value of the 6th term. So since this one stops at 5, we go to 6. So all you got to do is plug in 6. Now I don't even really care about the negative 1 because I'm going to be taking the absolute values. So all I'm looking at is 1 over 6 factorial. That's it. Plug in 6 in for your n. Absolute value of this is your error bound. Now, there's not going to be any negatives, so the absolute value is kind of moot at this point. So whatever that number, really, really small number, works out to being, that's our error bound. So the Lagrange error formula, which is sometimes just called the Taylor error, It's probably the toughest one, but it works in a more general sense. So this is always true of your Taylor polynomial. So this ends up being just the next term. So if you stopped at the nth term, you would do your derivative, your n plus 1 derivative, x minus some c value, right? N plus 1, the next term, over n plus 1 factorial. So it's just basically your next term of your variable. The variable z is a number between x and a is your basically your center value, and x is whatever number you're kind of using. You usually try to make your center value be close to your x that you're picking. So if you are looking for estimating f of 32, you wouldn't want to pick a center of 74. You want to pick something around 30, something like that. To determine whether the z value, so this z is the number that you're evaluating your derivative on, which is one of the trickier things. The z value will be the same as x or a. It's generally going to be that one of those two values. I've never actually seen it be a value in between them. It's almost always going to be that. However, the truth is you pick z to make this value a maximum. So if you follow the book, that's what it does, but then they never actually try to find the maximum of that. They just plug in the two endpoints and see which one ends up being the best. And again, a is basically your center, and x is the value you're plugging in. It's the actual number that you're looking for. So in this particular problem, your center would be, your a would be 0, and your x would be 0.1. Alright, so that's the trickiest part. Now, what you really want to remember from this, what will get you at the points, is for using a second degree Taylor polynomial, we have to be looking at the third term. So the error bound is our third term, so we take 6 over 1 minus x to the fourth, that's my derivative, times x, which is 0.1, minus a, which is 0, to the fourth, third, we're looking at third, we're starting with the second, let's add it up, third, all that over 3 factorial. Now the question is, what in the world do I put in here for this x? It really should be, technically based on the equation, z. So whatever the z value, I need to figure out whatever number is going to make this the biggest. Now I can plug in 0 or 0.1. So let's see, if I plug in 0, I get 6 over 1, which gives me, so this is when x equals 0, I get 6. If I use x equal to 0.1, see what I get. I get a 6 over 1 minus 0.1, or 0.9 to the fourth. Alright, so which one's bigger? 6 over 0.9 to the fourth, or 6? So we go to our calculator, we type that in. Well, if it was 6, anything 0.9 to the fourth is smaller than 1, but if you divide by something that's smaller than 1, it ends up making the number larger. So this is the value, but the truth is I got to use that value. That number has to go here. So we're going to go to our calculator here in a second and get that actual value. So I typed the numbers in the calculator. I know I had to jump this back over here. So if you lost the numbers that you're kind of looking for over here on the right, they're over here on the left. So we were looking for what 6 over 0.9 to the fourth was. So that's what we got, 9.1449, which is a whole lot bigger than 6. So that ends up being the maximum value. Now, you can go crazy with this and actually take the derivative of it and find out where your relative maximums are, or you could graph the function and look at an interval to see where they are. You feel free to do that, but I've never seen any book AP exam that would look at it anywhere other than the two endpoints. So that's our number that we're looking for. Actually, I correct that. There was one exam, and we'll talk about it in class at some point, where they give you a picture, and the picture was the next derivative, and it did something kind of like this. I feel like it's more bell-shaped, and so from the picture you had to pick off the maximum value, and that's what you ended up using here. So it does come up that they use the maximum more than this, but in that case where you had to actually use the maximum, I saw it actually on the graph, so I didn't have an explicit formula for it. So the next thing we do is we plug into the rest of our formula. We currently have our derivative satisfied. We found the maximum of that value. We take our x minus a to the n plus 1, so 0.1 cubed right here, divided by 3 factorial is 3 times 2 times 1, 6, and we get an error bound of that. So that's our Taylor error or our Lagrange error for that particular problem.